Okay, so moving on to part 2 here, we're going to start out with the theorem. So still 4-7. So we're starting out with the theorem, which is going to be the power rule for integrals. So basically what it says is if you integrate x to the n, if we think about it, this is saying who has derivative x to the n. So we're going to have to go back to n plus 1, because when you take the derivative of something with an n plus 1, the n plus 1 comes down, and you'll subtract 1 off the n plus 1, which will leave you an x to the n. But the problem is the n plus 1 came down, so we're going to need a 1 over n plus 1 out front, so that when this n plus 1 comes down, it cancels with the n plus 1 that's out there. And then we're able to add a plus c, and this works for all n's that are not equal to negative 1. So the end of the negative 1 works a different way, but this will be our power rule for integrals. So we'll look at a couple examples from the book of this. And actually, I guess we'll write down the one for next theorem, then we'll look at a few examples. So for this one, we say the function f of x equals natural log of absolute value of x is an antiderivative of y equals 1 over x in the domain set of all x such that x is not equal to 0. So in symbols, we could say the integral of 1 over x dx is equal to, well, since 1 over x, that was a natural log, this is going to equal natural log of absolute value of x plus a constant. So that's how we take the derivative of 1 over x. Antiderivative of 1 over x. That's how we integrate it. We also have the integral is linear, so linearity of the indefinite integral. This says if we have the integral of f of x plus g of x dx, we're able to view that as the integral of just the f of x part, and then we can add that to the integral of just the g of x part. So we're able to treat the individual terms independently and then add up their results. It also says if I have a constant that's being multiplied to my function f of x, I'm able to push the constant out in front of the integral like that. So this is linearity. We can use that. And now that we got our power rule, we have how to take the derivative of 1 over x, and we have linearity. We'll do a couple examples of taking antiderivatives. So for example 2 in the book, we're going to say take the indefinite integral of 3x to the 4th minus 5x to the 2/3 plus x to the negative 3 dx. So first I'm going to use the linearity, which says I can treat these terms individually. And I'm going to think about the x to the 4th. If I take I need something that when I take their derivative becomes x to the 4th. So I need an x to the 5th by the power rule. When the 5 comes down, it needs to cancel with a 1 over 5th. And then this is all multiplied out front by a 3. So when I take the derivative, the 5 comes down, 5 over 5 is 1, 5 minus 1 is 4, so this whole term becomes x to the 4th, and then it gets multiplied by 3. So minus, we have the 5, and now I'm going to deal with this part here. 2/3 plus 3/3 would be 5/3. The 5/3 is going to come down. It's going to need a 3/5 to cancel with it. And this will make this term here x to the 2/3, and then it gets multiplied by the negative 5. And this one, when we add 1 to -3, we get -2. The -2 would come down, so I would need a 1 over -2. So when the -2 comes down, it cancels. And then I need a plus constant because I can add any other number since the derivative of all numbers goes to 0. Like derivative of 10 is 0, derivative of 300 is 0. I put a plus c after it. So now I'm just going to try to algebraically clean up my expression. So I'd have 3/5 x to the 5 minus, the 5's can cancel here. We'll say 3 x to the 5/3 minus 1/2 x to the -2 plus c. And that will be our antiderivative. If we take the derivative of this, it turns into that. Could also say this is the indefinite integral of that statement there. So let's look at a couple more of these. We want to find the indefinite integral of 5 over x minus 3x to the -10 dx. So when I go to do this one, this is basically, we can use linearity, and maybe we'll write it all the way out in linearity. The 5 is a constant. It'll push out front of the integral symbol. So I'll be dealing with just the symbol 1 over x dx. We'd have minus 3 integral of x to the -10 dx. So when I go to deal with the integral of 1 over x, we saw that that was natural log of absolute value of x. We have minus 3 times the integral of x to the -10. That would be, let's see, that's x to the -9. And then we have a 1 over -9. So when the -9 comes down, it cancels out and you get to -10. We have the plus constant out there. So it looks like we get 5 natural log of x minus, it's going to be plus because minus and negative is positive. That'll be 1/3 x to the -9 plus a constant c. So if I take the derivative of this, it becomes that. Okay. We'll write down some of the trig laws and then we'll kind of pause here for a second. So trig integrals, if we have the integral of sine of x dx, that will equal negative cosine of x plus c. Integral of cosine of x dx, I think who has derivative cosine, that's sine of x. We have to put a plus constant after it. Integral of secant squared of x dx, that would be tangent of x. Derivative of tangent is secant squared plus c, because you can do tangent plus any other number, and its derivative still would be secant squared. Integral of cosecant squared of x dx. Derivative of cotangent was negative cosecant squared, so negative cotangent will have derivative positive cosecant squared. And the integral of secant of x tangent of x. The derivative of secant is secant tangent, so this will be secant of x plus c. And the integral of cosecant of x cotangent of x. Well, the derivative of positive cosecant was negative cosecant cotangent. So here if we have positive cosecant cotangent, that came from negative cosecant of x plus c. So we'll finish up with just two last statements here. If we want the integral of cosine of kx plus b dx, that would equal, so sine would be the, sine's derivative becomes cosine, but the chain rule would apply to a statement like this. It would be sine of kx plus b times the derivative of kx plus b would be an extra k there. So we need a 1 over k out front to cancel the k that gets sent out by the chain rule. So this right here is one way we can deal with that type of indefinite integral. And then if we have the indefinite integral of sine of kx plus b, for kind of similar reasonings, negative cosine, its derivative is positive sine. So we would have negative cosine of the kx plus b. The chain rule still applies. That's going to kick out an extra k. So we need a 1 over k to cancel the k that gets pushed out there. We'll have plus c like that. So these will give us two equations, and then we'll use them in the next example. So for this example here, this will be the last one I do of part 2. We want to evaluate the integral of sine of 8t minus 3 plus 20 cosine of 9t, all of that dt. So step 1, we're going to split up the integral using linearity. This will be the integral of sine of 8t minus 3 dt plus 20 is a constant, so it can go out front of the integral, cosine of 9t dt. So now we can use our formula and say, well, if you have kx plus b, the sine of the kx plus b, that'll turn into negative cosine with a 1 over k, which k would be 8 in this formula. So we'll get that this is negative 1 over 8 cosine of 8t minus 3. So the derivative of negative cosine is sine. Leave the inner part alone. When you take the derivative of the inner part, it would kick out an 8. The 8 will cancel with the 1/8, so you get sine of that. Plus, this will be 20. You want to do the one for cosine. It's going to be sine of kx plus b with a 1 over k out front. So k in this case would be 9. So it would be 20 times a 1 over 9 cosine of 9t. Whoops, sorry. Not cosine, it would be sine of 9t plus c. So the final answer, if we write it down a little bit nicer, 29th sine of 9t plus c. That would be our solution to that one. Again, it's got to be sine because the derivative of sine is cosine. So we'll stop there on part 2 and get the rest of it in a bit.